Dear friends, today we have to start with a new topic, redox potential diagrams. In the last session, we have seen about electrode potential or redox potential of a redox couple. Now we have to see how these potentials can be diagrammatically represented for the convenience of study and to make it more easy. At present, we have five kinds of diagrams with us. First one is redox predominance diagram. Redox predominance diagram. But actually it is not in your syllabus. Your syllabus start with second one, Latimer diagram, Frost diagram, Porbach's diagram and Ellingham diagram. All these diagrams can be seen as a representation of redox potential as a function of either oxidation number or the same thing can be represented in terms of free energy also. Latimer diagram actually is an advanced version of redox predominance diagram. So that purpose only we are mentioning redox predominance diagram first, even if it is not the part of your syllabus. In redox predominance diagram, we have to write the electrode potential in the increasing order, and parallelly we have to write the species in different oxidation number. Suppose A is the element, then A is in the 0 oxidation number and it has other oxidation number A plus, A2 plus, A3 plus, etc. For example, if we consider iron, it can have Fe plus 6, then Fe plus 3, then Fe plus 2 and Fe 0. Similarly, manganese have plus 7, plus 6, plus 5, plus 4, plus 3, plus 2, plus 1 and finally 0. So, for a given element, we have to write the easy rows in the increasing order and correspondingly species in the increasing order of their oxidation number. That is redox predominance diagram. When we come to Latimer diagram, this is a diagram. This is actually not a diagram, this is a writing of various species of the element in the increasing order of, decreasing order of their oxidation number. Suppose A is the element and A is expected to have 3 oxidation number of plus 1, plus 2 and plus 3. Then we can write A plus 3 at first, then to the right A plus 2, then again towards the right A plus, and finally at the extreme right we have A. Oxidation number decreases from left to right. Each series can be connected using an arrow mark. And on the top of the arrow mark, we have to write the electrode potential or redox potential of the diagram, corresponding species, redox potential of the corresponding species. E0, A3 plus bar A2 plus needs to be written over here. E0, A2 plus bar A plus needs to be written over here. This way we can write. This is the Latimer diagram. When we come to Frost diagram, this is the direct diagrammatic representation of Latimer. There we have to draw a graph between n is 0 against N. N is oxidation number, it is the product of oxidation number and E0. Then we will get a graph depending on the nature of the potential. That is Frost diagram. In power box diagram, we have to draw or we have to plot pH against electrode potential. pH against electrode potential. So that diagram is useful for studying the variation in the potential with change in pH. When we move from acidic to basic medium or neutral medium, how the potential varies. That kind of study will be beneficial for us to make an understanding on the corrosion for each and every metal. So for corrosion studies, we first understand the Pourbaix diagram, then only we can say this product is predominant at this condition of pH and other product will be predominant at other pH. And finally, you have studied Ellingham diagram in metallurgy. This is a plot of delta G 0 against temperature. Delta G0 is minus NFE0. So delta G0 is proportional to E0. So again it is a plot of E0 against temperature. So this kind of diagrams we have to represent diagrammatically the redox potentials of various species identified so far. First one, redox predominance diagram. For example, we have take iron. Fe, Fe2 plus, Fe3 plus, FeO4 2 minus in the increasing order of oxidation number 0, plus 2, plus 3 and plus 6, and their potential also written in the increasing order minus 0.44. So at minus 0.44, Fe and Fe2 plus are in equilibrium. At 0.77, Fe3 plus and Fe2 plus are in equilibrium. At 0.22, these two systems are in equilibrium. 7 you have been asked from 0.77 to 2.2, which is the most predominant species. Then you have the answer Fe3 plus. This kind of prediction can be done by this diagram, but it is possible if the change in redox potential is gradual. If there is any uncertainty, first decrease and then increase, or increase after that we have to decrease, under such condition this kind of a gradual increase cannot be observed, and under such condition it is impossible to draw redox predominance diagram. For example, Cu plus Cu2 plus, these are three species of the copper system, and for copper system Cu plus Cu are in equilibrium at 0.52. Cu2 plus and Cu plus is 0.15. So when we write it in the increasing order 0, 0.1, 0.2, 0.3 etc. up to 0.6, then oxidation number cannot be represented in the sequential order because here higher potential is at lower species and lower potential at the higher end. So this kind of condition cannot be explained using redox predominance diagram. Under such condition, it is better to use Latimer diagram. So we have to see what is Latimer diagram and what application these diagrams have. In Latimer diagram, as we declared in the first slide, write the various species of the element in the decreasing order of their oxidation number. From left to right, you have to represent the species in the decreasing order of oxidation number. That means highest oxidation number should be at the right and lowest oxidation number possible at the left. Each species can be connected using an arrow mark. Write the standard reduction potential of the couple on the top of this arrow mark. Fourth one, for reaction involving H plus. If a reaction involves H plus in balancing, potential of the system vary with pH. If there is no H plus or OH minus in the equation, that potential will be independent of the pH. That means in acidic medium and basic medium they have same potential. All these can be seen one by one in the examples. Greater the value of reduction potential, greater will be the tendency of species on the left to get converted to right. Redox potential value കൂടുതലാണെങ്കിൽ ലെഫ്റ്റിലിരിക്കുന്ന സ്പീഷീസ് റൈറ്റിലുള്ളതായി മാറാനുള്ള സാധ്യത കൂടുതലായിരിക്കും. റിഡക്ഷൻ പൊട്ടൻഷ്യൽ കൂടിയാൽ റിഡക്ഷൻ നടക്കാനുള്ള സാധ്യത കൂടും എന്നാണ്. ആൻഡ് ഫൈനലി, if the potential on the right is greater than the potential at the left, if the potential on the right is greater than the potential on the left, oxidation state seems to be unstable and they undergo disproportionation, which we have discussed in the previous class. Disproportionation is a kind of simultaneous oxidation and reduction. So it is the Latimer diagram for iron. Latimer diagram for iron. Iron can have +6, +3, +2 and 0 oxidation number under normal condition. But +6 is stable only at higher pH or in basic medium. So the highest oxidation number is written first or in the left. Then when we move from left to right, oxidation number decreases. That was the first statement. Second, you have to write arrow mark between each species. That was the second statement. And in third statement, we have told that redox potential of the couple needs to be represented above the arrow mark. So above the arrow mark you have to write the potential E0 Fe plus 6 bar Fe3 plus needs to be represented over here, that is in between these two species. E0 Fe3 plus bar Fe2 plus, that is to be represented between these two species, that is here. Here we have another potential of Fe2 plus bar Fe that you can see in the electrochemical series. This kind of representation is known as Latimer diagram. It is a case of iron. In the same way, you can have Latimer diagram for copper, chlorine, phosphorus, nitrogen, oxygen, and for any element you can write it. If you know the potential and various oxidation numbers possible for that particular element. The first was FeO42 minus and Fe3 plus, which has a potential of 2.2. Then Fe3 plus to Fe2 plus 0.77, Fe2 plus to Fe minus 0.44. In general reading, what we can say that reduction of Fe plus 6 to Fe3 plus is highly possible or is a rapid reaction. It is highly spontaneous reaction because of high reduction potential. This 2.2 is considered to be a significant and high value of reduction potential. That means Fe plus 6 can easily accept 3 electron and get reduced to Fe3 plus. In the same way, Fe3 plus can also have the tendency to get reduced to Fe2 plus by accepting 1 electron, and that tendency is 0.77 but it is less than this tendency. So FeO4 2 minus to Fe3 plus conversion is more spontaneous, and this conversion is also spontaneous from Fe3 plus to Fe2 plus, but that spontaneity level is somewhat less. Then Fe2 plus to Fe reduction is somewhat impossible because reduction potential is negative. So under normal condition, Fe2 plus will be the stablest species of ion. Under normal condition, Fe2 plus will be the stable species. If we have Fe, it corrode and tend to change into Fe2 plus. If we have Fe3 plus, it may also tend to change into Fe2 plus. So it is considered to be some of the one of the stable species in ion. Next we have Latimer diagram for copper. Possible oxidation numbers of copper are 0, +1 and +2. So we have to write them in the decreasing order of oxidation number, means Cu2 plus at first, then Cu plus and then Cu0, and corresponding reduction potential can be represented over the arrow mark. This is the diagram for copper. Now we have Latimer diagram for chlorine. For chlorine, we have two diagrams. First one at pH 0, that means in acidic medium. Second one at pH 14, means it is in basic medium. So we have two Latimer diagrams for chlorine, one in acidic medium and another one in basic medium. As far as concerned with chlorine, the highest possible oxidation number is +7 and lowest one is -1, which you have studied in representative elements of 5th semester. So we can write +7 at first, then +5, then +3, then +1, 0 and -1. In the same way, that is true here also. Corresponding potentials also represented here. In basic medium also you can see the corresponding potentials. In acidic medium, +7 to +5 change at a potential of 1.2, but here potential is only 0.37. Next change is seems to have different potentials. Next one also different potential. Another one, this is also different potential. But next one, Cl2 to Cl minus. Here also Cl2 to Cl minus both have same potential, 1.36 volt. So we are coming to the applications of Latimer diagram. First one, balancing of half cell reaction can start from a Latimer diagram. That means from the Latimer diagram we can see that ClO4 minus first converted to ClO3 minus. Then you have to write the skeletal equation ClO4 minus gives ClO3 minus and then balance it. Balancing you have studied in your +1 classes. Here oxidation number is +7 and it is +5. So it is a 2 electron change. Since it is a reduction process, electron need to be recorded at the left side, 2 electron. Here total charge is -3, 2 into -1, again -1, -3, here it is only -1. So charge can be balanced by adding H plus. Since it is in acidic medium, we have to use H plus. In basic medium you can use OH minus, here it is acidic medium. Then ClO4 minus plus 2 electron plus 2H plus. then charge is balanced. 2H plus 3 minus, then 1 minus will remain there, and here we have only 1 minus. Next one is balancing of oxygen. Here we have 4 oxygen, here we have 3 oxygen. ClO 3 minus, only 3 oxygen. So on, water can be added in that side where number of oxygen is less. Number of oxygen is less in this side, so we have to add 1 water here. Then balance hydrogen. We are lucky that hydrogen is already balanced, so we don't want to invest our time for balancing hydrogen. Second application, influence of pH on potential. Whether a reduction process is dependent or independent of pH, that can be predicted from this diagram. As we have seen in the Latimer diagram for chlorine, these two potentials are same. That means that potential is independent of the medium, but all other potentials are dependent on pH. This is the one which is independent of pH. That reaction is Cl2 to Cl minus. Then balance the chlorine. Cl2, we have 2 chlorine in the LHS, so we have to put 2 here. Then balance oxidation number. Cl2 plus 2 electron gives 2 Cl minus. Charge is also balanced, 2 minus 2 minus. No need to balance oxygen, no need to balance hydrogen. So this equation is the balanced equation. In this balanced equation, we have no H plus, we have no H minus. So this system is, potential of the system is independent of pH, or potential is same under all pH. Third one, calculation of skip potential. Potential of two non-neighboring couple. Non-neighboring couple. What is the potential of E0 Cu2 plus bar Cu plus? Definitely you have the answer 0.15. What is the potential of ECU plus bar Cu couple? That is 0.5. That can be directly extracted from the Latimer diagram as it represents there in the diagram. But if you have been asked to find the potential of E0 Cu2 plus bar Cu2 plus bar Cu, they are non-adjacent or non-neighboring couple. Such potentials are called skip potential. By skipping one species, we have to calculate the potential. For general example, we have the element A having oxidation number plus 1, plus 2 and plus 3. A plus 2, A2 plus, potential is E01. A plus 2 to plus 3, potential is E02. Then you have been asked to calculate E0 A plus bar A3 plus, here to here, here to here. To find out this potential, non-neighboring couple, potential of non-neighboring couple, we have to use the equation E03, that means potential of this couple equal to N1 E01 plus N2 E02 by N1 plus N2. N1, change in number of electron in first species. E01 means potential of that species, that couple. N2 means change in number of electron for second species. Then it's E0. Then total change in number of electron. For specific example, we are taking iron. FeO4 2 minus gives Fe3 plus, then Fe2 plus, then Fe, and correspondingly potential is also given. It you have seen in the previous slides. as the Latimer diagram for iron. Here if you have asked to calculate potential of Fe3 plus bar Fe3 plus bar Fe, a non-adjacent pair, non-neighboring couple, then we are writing E0 Fe3 plus bar Fe, they are non-neighboring. It is a two-step process. Then E0 Fe3 plus bar Fe2 plus, that is 0.77 into change in number of electron. For that reaction is 3 plus to 2 plus, 3 plus to 2 plus, 1 electron change. Then Fe2 plus bar Fe, this is E0 into change in number of electron is 2, 2 plus to 0, 2. Then total change in number of electron, 1 electron here and 2 electron here, total is 3. Substituting it, E0 Fe3 plus bar Fe equal to 1 change in number of electron into 0.77 plus 2 into 2 means change in number of electron in the second case plus potential is minus 0.44. 2 into minus 0.44 means minus 0.88 plus 0.77, that means 88 minus 77 minus 88, then minus 11 or minus 0.11 by total change in number of electron, first 1 electron in the first case, first step, and 2 electron in the second step. So 1 plus 2 is 3. 0.11 by 3 is minus 0.036 volt. This is the skip potential for E0 Fe3 plus bar Fe. Now next application is disproportionation or prediction of disproportionation. Normally we are expecting Latimer diagram like this. What is the peculiarity of this diagram? In this diagram, first potential is high, second potential is less. So potential in the right side is less than potential in the left side. Again low value. So as we move from left to right, potential gradually decreases. If this kind of gradual decrease can be seen in the Latimer diagram, there is no scope for disproportionation. But in some cases, potential in the right side is bigger than left side. Potential in the right side is bigger than left side. Then definitely disproportionation happen. Example, you are provided with Latimer diagram for oxygen. Various oxidation number of oxygen are 0, minus 1, minus 2. 0 in O2, minus 1 in H2O2, minus 2 in H2. First potential is 0.68, second one is plus 1.78, 1 not comma, 1.78, 0.68. Here potential on the right side is greater than left side. Definitely this species undergo disproportionation. Why? O2 has a tendency to get reduced to H2O2 since it is a positive value. H2O2 has a greater tendency to change into H2O since it is a bigger value. So this species is highly unstable. It will disproportionate gradually to this side and this side. So whether disproportionation is possible or not can be seen from the comparison of the potentials. If RHS is greater than LHS, definitely disproportionation of middle species will take place. H2O2 first get reduced to H2O, reduced to H2O. H2O2 to H2O. This is a reduction process because minus 1 to minus 2. So in reduction half we have H2O2 plus 2H plus 2 electron gives 2H2. That is balanced equation. If you don't know, you have to write it and balance. E0 value is given 1.78 volt. We have. Then H2O2 disproportionate. Disproportionation means reduction and oxidation at the same time. Reduction is completed. Then oxidation to O2. Minus 1 to 0, that is oxidation. H2O2 changes to O2. Then it is balanced and E0 is found to be 0.68 volt. Okay. This is cathodic reaction. Reduction is cathodic reaction and oxidation is anodic reaction. So in electrochemistry, it can be considered as a cell reaction. So total reaction is these species are cancelled. H2O plus H2O2 plus H2O2 to H2O2 gives 2H2O plus O2. This is a simple reaction and total EMF or E cell of this reaction can be calculated from E cathode minus E anode. Otherwise, E right minus E left. E right is or E cathode is 1.78 minus 0.68. So we will get 1.1. What is 1.1? E0 cell is 1.1. We have studied E0 cell equal to 0.0591 by n into log Kc. Log Kc. Kc means equilibrium constant. From that equation, log K equal to E0 into n. E0 into n by 0.0591. This is the equation. E0 is this one, 1.1. N is 2 electron change by 0.0591. On solving it, we will get 37.22. This is the value of log K. Then you have the question, what is K? You have to take the antilog of this number. Antilog of 37 is 10 raised to 37 and antilog of 0.22 is 1.66. So we have Kc equal to 1.66 into 10 raised to 7. That means this reaction have a good Kc or higher Kc. So it should have negative delta G. What is equation for delta G? Delta G equal to minus 2.303 RT log Kc. Here Kc is a highly positive value. Then its log also positive. Then delta G become negative. That process is spontaneous. So this disproportionation is spontaneously happening reaction. Since its Kc is high and delta G is negative. Suppose left value is higher and right value is lower. Then in the same way we will minus. Here we have subtracted 0.68 from 1.78. If it is 1.78, here it is, if it is 1.78 and it is 0.8, suppose condition is like that, then we have to reduce 0.68 minus 1.78, then value will be minus. If E cell is negative, log K will not be a value greater than 1 and delta G become positive value. Delta G equal to minus NF E0. If E0 is negative, negative of the negative will be a positive value. Then delta G become positive and reaction is not possible. Then under such condition disproportionation is not happening. This kind of disproportionation sometimes you can see in the diagram for chlorine also. Yes, you can see here in basic medium, please consider the diagram at the last end, that is ClO minus, Cl2 and Cl minus. Here you have 0.42 and here you have 1.36. Here value at the right side is bigger than left side. Then Cl2 will be unstable and disproportionate to Cl minus and ClO minus. This reaction you have studied in your degree classes, where you have seen it when chlorine added to water, it will disproportionate like this, HCl plus HOCl. HCl, this is HCl, this is HOCl. It was the reaction of bleaching action of chlorine, during which chlorine formed HOCl. Since HOCl is unstable, it will release, HOCl will release nascent oxygen. This nascent oxygen is responsible for the oxidizing action of chlorine or bleaching action of chlorine. That also you have studied. Basic thing behind that reaction is this disproportionation. So these are the major applications of Latimer diagram. Thank you.